All right, you guys, so I'm just going to try to quickly work through all these questions that are on the Unit 2 review. The test looks very similar, the same types of concepts, of course, so if you understand all of these, you should be good to go. All right, so the first page is refreshing on our parent functions, just like we did on our quiz the other day. So remember a linear function. All right, linear functions are the equation just y equals x, just a single x. You could also say f of x equals x, remember, because f of x is just a fancy way of writing y in function notation. All right, so and you can just type that into your calculator, into your y equals if you need to. All right, but that's just basically saying all the y values are going to equal whatever x values you put in. So, of course, if I put in a -2, I'm going to get out a -2. -1, 0, 1, 2. So if I plot these points to kind of see where my linear function is going, this is my parent linear function. And of course, don't just plot those 5 points. It actually goes on and on and on in that same exact pattern. Right, let me get that a little more straight. There we go, nice pretty straight line, going perfectly diagonal. Right, and so there is our parent linear function. You also need to be able to list the intercepts and the domain and range of each parent function. So of course it's crossing the x-axis at 0, 0. It's crossing the y-axis at 0, 0, 0, right? Because the parent function goes through the origin. It's going forever left and forever right. It's never going to hit a wall. So his domain is all real numbers. And the range is going forever down and forever up. So there is no walls that cut it off the height. So he's also all real numbers. All right, then we get into quadratic parent functions, right? And quadratic parent functions are y equals x squared, or f of x equals x squared. Either way, it's the same thing. So that means whatever I get out for y is just the x value squared. So if I put in a -2 squared is +4. Please use parentheses if you're squaring things in your calculator. -1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. So these are our initial 4 points that are going to help us draw a nice accurate graph. Please do not just draw some random U-shaped graph, right? When you draw a function, it needs to be very deliberate, and the points need to be, I will be checking to make sure that they are in those exact spots, right? There's no just drawing some random parabola and expecting to get credit for it, right? We want a perfect little U shape going through those 5 points. So obviously he's also going through the origin. So his x and y intercept are 0, 0, and 0, 0. I don't really know why the domain and range aren't on here, but I guess we'll get to that later. All right, exponential parent functions. All right, so the exponential parent function, remember it's called an exponential function because the exponent is the x, right? So 2 to the x power. Again, you can use your calculator for this, right? You can either go to the y equals button and then type it in, or you can and go look at your table, or you can just literally just type in 2 raised to the -2 power, which is 0.25 or 1/4. 2 to the -1 power is 0.5. 2 to the 0 power is 1. 2 to the first power is 2, and 2 to the second power is 4. Right? And so we can plot those points to get us a general idea of what that graph looks like. Again, you must be very deliberate in your points, not just drawing some random curve that looks kind of exponential. Right? Remember, exponential functions are the ones that have the asymptote. Right? Sorry, let me get an orange line. So remember this guy, every exponential function has an asymptote, right? Every exponential function has an asymptote, right? A line that it's going to approach but never ever get to. The parent function, his asymptote is the x-axis, right? So he'll never reach y equals 0. We'll talk more about that in just 1 second. So of course the x-intercept, there is none, right? Because he never will get to the x-axis. The y-intercept is of course 0, 1, which we're totally getting right here in the table. And the graph, right? There's 2 ways for us to see that. All right, this is pretty much what the first page of your test looks like, right? Again, being able to graph all of those parent functions and know their equations. All right, this next bit, discrete or continuous, and state, domain, and range, and whether it's a function or not. All right, so remember, first let's talk about discrete versus continuous. Discrete means all you have is a list of points, right? You're not including all the infinite decimals in between. It's just a list of points. Continuous is going to be an actual line. It's all connected, right? And we're including all the infinite values. So clearly on number 4 here, it's just a list of points. So this is going to be discrete. All right, so it's discrete information. The domain is your x values in order from least to greatest, right? So my x values are 1, -2, 0, and 3, -3. But remember, when you list domain, you are doing it in order from least to greatest and with no repeaters, right? So there are no repeating x's. So let's see, -3 is our smallest x value, then -2, then 0, then 1. Right. And then, of course, we want our range values, which is just simply a list of all of the y's. Sorry about that. There we go. In order from least to greatest. Notice the 4 appears twice, but when I write my range, I'm only going to write it once. So it looks like the lowest y is 3, and then 4, and then 7. So there's my list of y's in order, least to greatest, no repeaters. And then is this a function? That would be a yes, right? Because there are no repeating x's. Right? The x's do not repeat. So that means every single x has a unique y output. So that is yes, a function. All right, basically the exact same thing over here, right? T is definitely discrete because, again, it's just a list of points. My x values, and again, please use, highlighters on your test tomorrow. It's really helpful to kind of make sure your eye is only going to one spot. So my domain from least to greatest is going to be -4, 1, and of course the 5 is mentioned twice, so I'm going to only write it once though. And then our range, right, we've got a 3, a 7, a 7, and a 9. Nicely, that's already in order from least to greatest. So 3, 7, 9, because I don't want to put the double sevens. I only need to mention it once. And is this a function, yes or no? That would be a no, right? And the reason it's not a function is because I can't put in a 5 and get out a 7, and then put in a 5 and get out a 9, right? I can't get two different y's for the same x. Okay, so that is why it's a no. All right, it looks like our next, number 6, is also just it's an XY table, so it appears as if only these 4 points are on our graph, right? Remember, an XY table is just like an organized set of points, just like the previous 2 problems, right? So it's definitely discrete because it's just a series of points. The domain, of course, is all of the x's, right? Just listed in order from least to greatest. Sorry, I'm taking me a while to go back and forth between the colors. So 0, 1, 2, 3. And then the range, which would be the y's in order from least to greatest. Now in the table, they're mentioned from greatest to least, but that does not matter. When we write the range, it's always least to greatest. There's no repeaters, so we didn't have to worry about that. Is it a function? Yes, it is. Right? The x's do not repeat. Right? Every x has its own unique y. So that is definitely a function. All right. Number 7. The fact that this is a line, and like if I wanted to draw this with my pencil, I'd start here and then go up. Right? That is a continuous graph because I'm clearly including all the infinite decimals all along the way from my 2 endpoints. So this is definitely continuous. The domain is going to be all the x values that this graph takes on. Now the thing is, right, if you talk about, is this graph allowed to go forever to the left? No. Is he allowed to go forever to the right? No. He's not even allowed to go left or right. Oops, I want to highlight. And the reason why is because he's only allowed to be one x value and one x value only, and that would just be -3. And that is his domain, right? That is the only x value that he's allowed to be. Then when we get to the range, right, floor to ceiling, we're asking ourselves, can this guy go forever down? No, because he's hitting a wall, right? And that wall is occurring at a y value of -5. And then is he allowed to go up forever? Nope, because he hits a wall here, and that has a value of 3. So all of our y values exist between -5 and 3. So remember, if there's two walls, that means there has to be two inequalities, right? Double wall, double inequality, right? So from low to high, my y's are between -5 and 3. And remember, when you have a double inequality, these are always less thans because you're always writing the expression from least to greatest. You just have to figure out, is it going to have equal to bars? Well, at -5, oops, sorry about that. At -5, yes, I'm totally equaling -5 because of the solid dot, right? So that means we're going to have an equal to bar. But then at y equals +3, I see an open circle. And that means we actually can't equal 3. We're just going right up to 3. 2.999999999, but I can't actually ever hit the 3. Is it a function? That's a big no, right? Because this fails the vertical line test. I'll write that down. Fails the, I'm just going to put VLT, vertical line test, like we talked about in class. Remember, a vertical line is the biggest failure of the vertical line test ever, because the vertical line test says if you can draw a vertical line anywhere on the graph and it hits it at more than one point, then it's definitely not a function. And if I draw a vertical line, I'm hitting every single point on that graph, right? So definitely not a function. Which makes sense because I'm putting in the same exact x value and I'm getting different y's the entire time. All right, next up, definitely continuous, right? Because it's not just a series of dots, right? It's actual connecting dots and including all the infinite decimals in between. Right, the domain, let me get my pink back. I'm getting my highlighters. Is he allowed to go forever left? Nope, he hits a wall, and that wall has an x value of -4. Is he allowed to go forever right? Nope, he hits a wall, and that wall has an x value of 5. So all of my x values exist between -4 and 5. So that is exactly what we're going to write down in our domain. All the x's exist between -4 and 5. Double wall, double inequality, so these are always less thans. And then it's just a matter of, can we use the equal to bar? Clearly there's an open circle at -4, so we can't equal that. But there is a closed circle at +5, so we can equal that value. All right, and so that would be our domain. All right, now we got to do the range, which is floor to ceiling, right? Does this graph go forever down? Nope. He hits a wall, and that wall has a y value of 1. And can he go forever up? Nope, because he has a y value of 3, right? So all the y values exist between 1 and 3. So 1 is less than or equal to y is less than or equal to 3. And then, of course, you're looking at the y value. Can he equal +1? No, because of the open circle. Can he equal +3? Yes, because we have a closed circle. So we're going to make sure we put an equal to bar by the 3. Is it a function? Yes, right? He definitely passes the vertical line test, right? Everywhere I draw a vertical line, he only hits the function one time. Okay. All right. Determine if it's discrete or continuous and explain your reasoning. The number of bananas purchased depends on the number of monkeys you need to feed. You don't have to make an XY graph or anything, but I'm just going to do that because we did this in our notes. So remember, the dependent variable is always the y. So the number of bananas, all right, so I'm going to put that here. Number of bananas depends on the number of monkeys. So number of monkeys has to be the x. And where do we always, what variable do we always look at to figure out if it's discrete or continuous? The x. I don't care about the y. I care about the independent values that I'm plugging into this function, right? And my independent variable is number of monkeys. So is that going to be discrete or continuous? Well, is there any such thing as 3.75 monkeys? I can't have a fractional monkey. That would be disturbing, right? So monkeys can only come in whole numbers, right? There's 1 monkey, 2 monkeys, 3 monkeys. I can't have 6.5 repeating monkeys. All right, so I'm not going to be using fractions. So I'm going to say continuous. I'm sorry, I don't know why I just wrote that. Oh my goodness. Okay, so discrete, so sorry. I almost didn't catch myself. Right, discrete, and you can write a couple different reasons. You can write, you can only have whole numbers of monkeys. You can write you can't have fractional monkeys, right? Either way, right, I'm going to write you can't have fractional monkeys. Or if you want to approach it from the more positive side, right, you can only have whole numbers, right? Whole numbers only. All right. Our next one is the number of gallons used depends on the number of miles you drive. So I would assume we're talking about gasoline. All right. And so number of gallons. That's not a very good graph. Let me do this. All right. So if it depends on. All right. And this is going to be number of miles. All right. Based on that graph. And then, of course, we only look at the x to figure out if it's continuous or discrete, right? And you want to ask yourself, can I drive fractional miles, right? Can I drive 6.25 miles? Can I drive 8 1/3 miles, right? Yes, right? So this is continuous. And I'm going to say you can drive fractional miles. And again, you don't have to write exactly what I do, but just something along those lines. All right, distance you run depends on the time spent running. Okay, and again, you don't have to draw the graphs. I'm just doing this to help us understand where these things go. So your distance, which would be your dependent variable, depends on the time you spend running. And that could be minutes, that could be hours. I guess that depends on how long you're running, but it doesn't really matter because time is always continuous. Right? Time keeps going. I can have fractional time. You can have fractional time. All right, I can run for 6.3 minutes. Sorry about that. All right, next up. We didn't do a whole lot of these in class, so you're going to want to pay attention to these right here. It's nothing that you shouldn't be able to handle, right? These are on your test, though, so you want to make sure you're paying attention. What this is asking, none of these, I repeat, none of these are the parent function, right? But they are children of a parent function. So they're part of the family of a certain parent function. So you just need to figure out what family they belong to, right? So on number 12, clearly the parent name would be exponential. This is very obviously an exponential function, right? Because we have a curve, right? It's coming down. And what do all exponential functions have? Asymptotes, right? So our asymptote on this one is always going to be the line that it looks like it's reaching, but it's never getting there, right? So this is actually my asymptote right there, right? And the reason why you need to know that is because on here, it's asking you to find the zeros. Remember, zeros, this is in our notes, zeros is just a fancy name for x-intercepts. We're going to start using them interchangeably because you need to know all the synonyms for x-intercepts. Zeros, roots, solutions, x-intercepts, right? They all mean the same thing. Okay, so that was all written in our notes. So it's asking, where does this guy cross the x-axis? Well, he clearly doesn't because he's not even crossing x equals 3. Y equals 3, right? Because we have this asymptote. So he's never getting to that x-axis, right? He's even further away than the parent function. So this is none. And then, of course, we need to find our y-intercept. Every function has a y-intercept, right? And in this case, it's going to be that 4. But we don't just want to write 4. Remember, you should always write your intercepts as ordered pairs, 0, 4. All right, this guy, what function family does he belong to? He is clearly a linear function, right? So he belongs to the linear family. Now, he is not going to have the same x and y intercepts as the parent linear function because he's not the parent linear function. So you actually need to go find the x and y intercepts of this particular linear function, right? And the x-intercept would be this guy right here. Make sure you're paying attention to the units, right? Because if this is 2, that means this is 1. So every other one is like a half, right? So I'm skipping every other one. So this would be 3. So pay really close attention, right, to the scale that the axes are going by. So my x-intercept is 3, 0. Again, don't just write 3, right? Make sure you're writing the whole point, 3, 0. And then the y-intercept is where he's crossing the y-axis. And again, same thing, right? This would be -1, -2, etc. So my y-intercept is 0, -1. All right, and then on this last guy over here, what family does he belong to? Well, he's a U-shaped parabola, so he is clearly a quadratic function. Again, he's not the parent quadratic function, but he is a quadratic function. He's in that family, right? And so notice it's asking us to find the roots, which again is just a synonym of x-intercepts, right? And remember, a function can have more than one x-intercept. It cannot have more than one y-intercept, but it can have multiple x-intercepts. It can have no x-intercepts, but you do need to know that roots is just another word for x-intercepts. So when I go figure out, looks like it's crossing the x-axis here and here. And if I'm paying attention to my scale, that looks like -3 and 1. So I'm going to write that as -3, 0 and 1, 0 because he has 2 roots or 2 x-intercepts. And then my y-intercept is clearly right here, right? And again, paying close attention to that scale, right? That's a +3, so that is the point 0, 3. All right, so make sure you can, even though these aren't parent functions, we should still be able to figure out what family the function belongs to when we look at the graph. All right, the next part, find the range of the function if the domain is -5, 0, 1. So they're clearly giving you 3 different x values. Remember, domain is x values. So they're basically asking you to plug in each one of these numbers in for x and then solve for y, or f of x, right? So it's a 3-part question. So here we go. F of -5 means I'm going to go to my f function, and all I'm going to do is plug in -5 in for x. And then I'm going to you can either type that in your calculator, right? We're just literally evaluating the function, right? So 5 minus 2 times -5, right? So that's actually going to be 5 plus 10, so that should give us 15. Then I'm going to plug in f of 0, so 5 minus 2 times 0, which gives us 5. And then we're going to plug in f of 1, so 5 minus 2 times 1, which will give us 3. Right, and so these are my range values right here. If you want to, you can write that as 3, 15, 5, and you can put it in a set of curly brackets. You don't have to do that, though. I'm really just looking for you understanding that you are getting these 3 y values when you plug in those 3 x values, right? So we're just literally taking the x value and plugging it in. And you're doing that just on every single one of these. It's the exact same question over and over and over again. All right, so I'm going to fly through these pretty quick. G of -5 equals 7 plus -5 squared. If you do not put parentheses around that in your calculator, you are not going to get the correct answer, right? We've said that a million times in class, right? Anytime you put a number in a calculator for a variable, it should always be in parentheses, no matter what, 100% of the time. All right, so that's going to give us +25 plus 7, so 32 is what we should be getting for that output. G of 0, so 7 plus 0 squared, which is clearly just going to give us 0. And then G of 1, so 7 plus 1 squared, which will give us 8. All right, and so these are the answers we are looking for. All right, those are my range values when I plug in all the x's. If you want to get all fancy and put them in numerical order and write them in some curly brackets because we're finding range, you can totally do that. All right, and last but not least, doing it one more time, h of -5, 4 times -5, does that say minus? Yep, -2. So that's going to give us negative 22. And then h of 0. So 4 times 0 minus 2. All right, which is going to give us negative 2. And then h of 1. 4 times 1 minus 2, which will give us positive 2. So here's our range values that we get, our y values when we plug in those x's. And once again, if you want to get fancy and put it in order from least to greatest, you certainly can. All right, so they're giving you the x's. We're finding the y's. Just 3 problems in one. Okay. This part is basically the exact same, except you're given an h function, an f function, and a g function. So you are going to use the function notation to figure out what function you're going to. So number 18 says f of negative 3, which remember is just a set of instructions that are telling you to go to the f function and plug a negative 3 in wherever you see an x. So f of negative 3 is 12 plus 2 times negative 3. I'm just going to bring that down here. So 12 minus 6 is going to give us 6. Right, and you can just write 6. You don't have to write f of negative 3 equals 6, even though that would be great. All right, same thing. Next one, g of 8. That means go to the g function, and everywhere you see an x, you're going to put in an 8. Now remember, g of 8 is just function notation. Right, please do not think that this means g times 8. This is just a fancy way of saying y. Right, but we're just naming the function with a g and telling what the input value is. And then 2 times 8 squared. And again, please use your calculator. If you're not sure about your math, you have to do exponents first. So that's going to give you 64 times 2. So 128 is going to be our g of 8. Let me box that up. There we go. All right, change colors. h of 0. That means go to the h function and plug a 0 in for x. So h of 0, 7 minus 3 times 0. And then you're just going to do the math on the right-hand side. 7 minus 0, obviously, is just going to give us 7. Now this number 21, we actually haven't done this one, but I just threw it on here anyway. This is called a composite function, which we don't talk about for a little while, but it's actually pretty easy. You just always work it from the inside out. Hold on, let me write that down. So it's a 2-part problem. Work from inside out. So it's a 2-step problem. The first step is we're going to go find g of 3 because he's the inside. So that means we're going to go to the g function and we're going to figure out what g of 3 is. So g of 3 is 2 times 3 squared. So g of 3 is 18. All right, but we're not done because now we're going to go find f of that answer we just got. Well, if g of 3 is 18, that means now I'm going to go find f of 18. All right, we're using the output of g as the input of f. So now it's telling me to go to the f function and put an 18 in. So 12 plus 2, but instead of x, we're going to put in an 18. And so that is going to give us, 36, so 48. All right, for our final answer. Voila. Okay, so just kind of 2 problems in one, nothing too crazy. You just do the inside one first, and then you take that output and put it into the other function that's on the outside. All right, moving right along. We're going to answer these questions. All right, these are the ones that go backwards, right? So you just really want to be careful. It says find the value of x, right? So that f of x equals 16. So remember, this is the y. They're basically telling you y is 16. So you're going to go to the f function, and wherever you see an f of x, we're not plugging in for x anymore. We're plugging the entire value in for f of x. So I'm going to completely rewrite that f of x function, but I'm going to put the 16 in place of the y. And then I'm going to solve that 2-step algebra equation for x. right? So we're just going to subtract the 12 from both sides, right? We're right back to unit 1 here, right? So we're going to subtract the 12 from both sides, which gives us 4 equals 2x. And then we'll divide by 2 on both sides. And so we're going to get x equals 2. That is the input that gives us the output of 16. All right, so this one's going in reverse, right? They're not giving us the x value, they're giving us the y value, and we have to solve for x. It's a lot more work to go backwards than it is to just plug a number in for x, so I can just type it in my calculator, right? When you're given the output, you have to do all the solving work, right, and figure out what the x value is. Okay, same thing on the next problem. Find the value of x, so that g of x is 32. Again, that's just saying you're going to go to the g function, right? And wherever I see a g of x, I'm going to plug in a 32. So I'm going to rewrite that equation. 32 equals 2x squared. Now be careful here. We talked about this in class. It's kind of a weird scenario because we're solving for x, but he's squared. You must get the x squared all by itself before you do anything else, right? So I have to divide by 2. I do not have a choice, right? You have to get the x squared all alone before you do anything else. So I'm going to divide by that 2 multiplier. And then remember we talked about this in class, right? If I want to undo a square, then I square root both sides because square roots and squares cancel. But remember, when you solve by square rooting, you're asking yourself what number is, what number squared gives me positive 16. And that's not just positive 4, that's also negative 4. And you are responsible for remembering that because your calculator is not going to spit out the negative version of that square root, right? So you need to make sure that when you solve by square rooting, right, there's always going to be 2 solutions. Okay? We'll talk about that much later, right? But that's just kind of, planting the seed in our brain for later. All right, next up is the arithmetic sequences versus the geometric sequences. So remember, all in arithmetic sequences is, and I hate the way that's written. Somebody doesn't know how to do subscripts. So remember, that's a little subscript. A sub n equals a sub n minus 1 plus the common difference. Right, that's actually what those should look like, right? Those should be little subscripts. All right, so I'm just going to write that next to it. Right, same thing over here. A geometric sequence is when you have a multiplier called the common ratio. Right, and again, that should be written with subscripts. A sub n equals a sub n minus 1 times whatever that common ratio is that you're multiplying every time. All right, so the first part of this is to determine if it's arithmetic or geometric and then write the rule, right? These are the rules right here, right? When it says write the rule, it's writing the a sub n, blah, 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 and you're finding the common ratio and the common, or the common difference. All right, so here we go, 3, 14, 25. Well, let's see. I always check for adding first. So the numbers are getting bigger. So I always check to see if I'm adding. So from 3 to 14, it looks like I'm adding 11. And then from 14 to 25, oh yeah, I'm adding a number 11. All right, so that's our common difference. So this is definitely an arithmetic sequence. I'm going to write that down because it has a common difference because I'm adding to get from one number to the next. Right? But it also wants the rule. So a sub n equals a sub n minus 1 plus 11. Or if you want to write the plus 11 in the front of the a sub n minus 1, you certainly can. It doesn't make a difference if you put the plus 1 at the front or the back. Over here, these numbers are getting smaller and very quickly, so this is definitely geometric, right? And I know that because I'm definitely dividing by 5. But instead of thinking divide by 5, I actually want to think about the multiplier, which would be times a fifth, right? Dividing by 5 and multiplying by a fifth are the exact same thing, right? And so that is my common ratio. So this is a geometric sequence because I'm multiplying by something to get from one term to the next. And then my rule would just be a sub n equals a sub n minus 1 times 1/5. Or again, you can put the 1/5, let me change that 5, that looks really weird. If you want to put the 1/5 multiplier in front of the a sub n minus 1, you can. It doesn't matter where you put that multiplier. All right, we're almost done. Zhu has $15 to spend at lunch. There is a stand selling tacos for $3 each. If X represents the number of tacos you can buy and Y represents the amount of money he has left, what would be a reasonable domain and range? All right, we talked about this in class the other day. I highly suggest that you make a table of values for these. You don't have to, but it's totally a good idea, right? And the cool thing is we're not making you figure out which is the X and Y, right? They tell you, right? X is the number of tacos. So let me zoom in here. Number of tacos. And then Y is the amount of money he has left. So we just want to come up with reasonable, and I don't really know how many values I need in my table, so I'm just going to kind of start it. Obviously, can you go in and buy 0 tacos? Sure, that's reasonable, right? Maybe he walks in, he's like, I don't want tacos today, right? And so that means he's going to keep all $15 in his pocket. Could he go buy 1 taco? Sure, and if he does, they're $3 each, so he would have $12 left in his pocket. If he goes and buys 2 tacos, he'll have $3 less, so he'll have $9. If he buys 3 tacos, he'll have $3 less, so he'll have $6. If he buys 4, he'll have $3 left. Can he buy any more tacos? Yep, I need one more. A little wrong to my table here. All right, looks like he can afford to buy 5 tacos, but that would take all of his money. Right? So it's just an easy way to kind of think about reasonable values for the situation at hand. But you also need to ask yourself, is this discrete or continuous? Right? And remember, we always go to the X value for that. Right? Can he go into the store and say, I want 6.72 tacos? No. Right? So this is discrete data. This is going to be a discrete graph, which is only going to consist of these 6 points. Right? And once I realize that, then now I'm good, right? Because I've already done my table. So I've already found my domain and range. My domain is anyone, 0 tacos, 1, 2, 3, 4, 5. And my range is how much money he has left from least to greatest. Oopsies. I like to have a line. There we go. So he could have $0 left, $3 left, 6, 9, 12, or keep all 15 of his dollars. All right, and that would be the reasonable domain and range. All right, next up, Timmy is 20 feet from the guards. He knows they'll take at least 30 seconds to discover he is missing, but no more than 120 seconds. Timmy can run at 18 feet per second. Write an inequality to represent the domain and range of this situation. All right, the reason, don't be tricked, right? The reason it's telling you to write an inequality, that is your clue that they're already telling you that this is continuous, right? Because we're talking about seconds, and we can have fractional seconds, right? So the fact that they said write an inequality means that they're telling you that this is a continuous graph, okay? All right. In this case, let's see. I'm going to kind of draw a graph on this one, if everyone's okay with that, as opposed to a table. You can kind of do either one. But we know this is going to be seconds, right? The x-axis is going to be seconds, right? And this is how many feet he is away from the guards, right? So he's starting off at 20 feet away from the guards, right? That is his starting amount. So when x is 0, right? He knows they will take at least 30 seconds to discover he's missing, but no more than 120 seconds. Now, that's kind of confusing the way that's written, but all that's telling you is that these are your x values. At least 30 seconds, but no more than 120, right? So here's 30, and here's 120. Okay. All right. Now, it says Timmy, this one's kind of a lot more confusing. This one also says that Timmy can run 18 feet per second. 18 feet per second. That's a lot. I feel like that's a typo. All right, so hold on. I feel like there's a typo there. Okay, I feel like I just put my 20 too high. I think that's just misleading me. Sorry, let me fix my graph really quick. I apologize. There we go. All right. So sorry, the weird thing is he's running away from the guards, so his distance is increasing, right? So here's my 20. There we go. So basically my graph is going to look something like this, right? He's starting here, and then he's running right here, right? His distance is increasing, right? He's 20 feet from the guards. He's running away, right? Now what you have to figure out is what is this y value right here? Well, we know that he runs 15 feet per second. So we actually can write the algebra equation y equals 18x. Sorry about that. All right. So if I know he is going to have no more than 120 seconds, that's my x value that I'm going to plug in. So y equals 18. This is why I'm not making a table, because my numbers are going to get really, it'd be a really big table. So I'm going to do the graph instead. So how far away is he after 18 seconds, right? 18 times 20, right? 18 feet per second. So after, I forgot my one. Sorry about that. So after 120 seconds, 120 times 18, I'm going to use my calculator for that. He is 2,160 feet away. That is quite far, right? So after 120 seconds, he's 2,100, I'm going to put that right here, and 60 feet away. All right, so that means my domain, all right, here we go. My reasonable domain, remember, is all the x's. Well, does this graph go forever left? No, right? It's everything between 30 and 120. So that's my domain, right? My x's are everything between 30 and 120. And then my range is going to be our y values. I feel like I totally misread this question. Here we go. And our range goes from 20 to 2160. That does not make any sense. 30, hold on. Oh my gosh, I've totally flipped up that entire problem. Okay, I'm so sorry. This is what being sick does for you. All right, so, oh my gosh. I'm going to completely erase this. Ugh. Ignore. Please rewind. Go back. Oh my gosh. Okay. Let's make this easy on ourselves. I don't know why I just made that so complicated. Here we go. So clearly our equation, oh my gosh, sorry about that, y'all, is 18 feet per second, right? So I know that my x value, my equation is y equals 18x, right? But he's already 20 feet from the guards, so I have the 20 feet also. If you want to write that in reverse, which would probably make more sense, so he starts off 20 feet away already, plus he's adding an additional 18 feet per second after he's already 20 yards away. All right, hopefully that makes sense. Okay, so basically, domain, we automatically know that the reasonable domain is going to be my x values are between 30 and 120 because they gave us that in the problem, right? Now, all you have to do, I'm not even going to make a graph. I'm not even going to bother. All right, all you got to do is figure out what y values correspond to these extremes of 30 and 120 for your x values, right? So essentially, I'm just going to take that x equals 30, and I'm going to plug it in, right, and see what I get for my y value there. Right, so 20, I'm typing it in my calculator, 18 times 30, just so I don't make another dumb mistake, is 560. So after 30 seconds, he's going to be 560 feet away. That's what corresponds to the x equals 30. Then we want to take our equation and plug in the 120. All right, so 20 plus 18 times 120, which is going to be a really big number, of course. So 2180. All right. I don't know why I was attempting to draw the graph. My y-intercept was not even correct. Sorry about that, y'all. So yeah, you can make it. I obviously don't want to make a table because obviously the numbers are massive and my table would go on forever. So it's not like the previous problem where I'm just talking about a finite number of tacos, right? This one's a lot easier to just write the algebra equation and then use the given domain because they already provided that for me in the problem, right? Let me highlight this, right? This is that domain, right, that they gave us here. So they already gave you half of the answer just in the problem. Okay. All right. God, I'm so sorry. I hope that makes sense. All right. The last one. Timmy is 350 miles from home. He's driving 70 miles an hour. He passes the time by pondering as to his next steps upon arrival. If X is the number of hours Timmy has been driving and Y represents the miles he has left to travel, create an inequality. Boom. Again, telling you it's continuous. Right, your domain and range should have less than and stuff like that. That describes the reasonable domain and range of this situation. Okay, if you want to, you can make a table for this. You don't have to. Again, it's kind of lengthy to draw a table, but I'll do both since I totally flubbed that other problem. Sorry about that again. All right, so we know this is number of hours he's been driving and miles from home. That all in the box. There we go. All right. So clearly it says Timmy is 350 miles from home. Okay. So if he's not driving at all, right, that means he, after 0 hours, he is still 350 miles from home. Right. He can drive 1 hour because he's driving 70 miles per hour. Right. That means he's going to be 70 miles closer. Right. So this will give us 280 miles away from home. And then after 2 hours, he's going to be 70 miles closer. And then after 3 hours, he'll be another 70 miles closer. And then after 4, he's another 70 miles closer. And then at 5, he would make it home. So I don't even need this table anymore, right? Because it wouldn't be reasonable for me to add a 6 to my table of values because he's home, right? So keeping in mind that this is continuous, we just want to make sure we remember that our domain and range should be written as an inequality, which the problem is already prompting you to realize. So my x values are everything between 0 and 5, and the range is going to be everything between 0 and 350. All right. Now, if you want to write an equation, you totally can. Right? It says he's 350 miles from home and his distance is decreasing by 70 miles per hour. So that would be our equation. If you want to use the equation, you could, of course, use the equation to figure out how long it's going to take him to get home, right? Which is clearly 5 hours, right? And you can also use that information. I don't know where my 0 went here. Sorry. There we go. To figure out that his distance from home is going to be from 0 to 350. For me personally, I just think it's easier to do a table of values if my numbers are going to be relatively small, unlike that number 27. All right. I hope that makes sense, everybody. Feel free to email me if you have any direct questions before test day. Okay? All right. I will see you guys tomorrow.